Yeah, I'll give you guys a bit more time. Okay, actually time's up already, but 2 more minutes. 2 more minutes. Okay, the last part of the question can get 1 mark. Okay. So we're just going to draw something. The drawing isn't hard. You get 1 mark. No, you don't change the wedges. You only change the groups. So the wedges like that don't make sense. Whatever that is closer to you, right, will be pointing outwards. Whatever that's further from you. So like, solid bonds are pointing outwards towards you, right? So you should be facing, you should be closer to you now, which is bottom to. You shouldn't be doing it. It doesn't make sense. Like that. So you don't change the position of the wedges. You only change the position of the groups on the.
But for like
Mandumas,
you don't shift either, right? You just
yeah, you never ever shift the wedges. The wedges are always on the same positions. Yeah. Okay, but when you flip it in the mirror image for enantiomers, then that one's slightly different. That one you flip, you just swap the two groups. As I'm talking about the square planar shape. Square planar shape is whatever that's closer to you should be pointing outwards. Yeah. Okay, I'm just going to go over the answers. Okay, so give you guys enough time for just nice. I think this all these parts are okay. So come, let's take a look. Okay, for part 1 answer, right? Okay, you just need to read the question a bit carefully. Okay, when your temperature increases, okay, your proportion of G to F increases, right? Okay, so that means your G increases and F will decrease instead. Okay, that's how the proportion increases. Okay, so in other words, this question is asking us to take a look at the position of equilibrium. If your G increases and F decreases, what does that mean about the POE? Where must it have shifted towards? The right hand side, yes. Okay, so when you have shifted towards the right, you are favoring the forward reaction, right? Okay, so you can just mention all these things in your answer also. Okay, you first tell me what you observed in the question. Okay, and your observation must mean something. So the POE must have shifted right. And what does shifting right mean in terms of finding out whether it's endothermic or exothermic? Okay, so again, shifting right means the forward reaction has been favored. Okay, but you need to identify the forward reaction here, is it endothermic or exothermic? Endo, right? Okay, because when you increase temperature, you always favor the endo reaction, okay, to absorb heat. So you need to mention all these typical keywords when it comes to the Chladnius principle. Right, okay, so forward endothermic reaction was favored to absorb heat. And even after writing all these down, right, okay, for 1 mark, okay, it's a bit demanding because they ask you guys to answer the question. Okay, what's the sign of your Y? Okay, you must tell me when Y is positive. You can tell me a whole chunk of correct answers, but if you don't answer the question right, at the end of the day, they can still not give you that 1 mark. Okay, so just be very careful. Okay, everything must be inside. Yes. Okay, absorb and remove, same thing, yes. Okay. Now moving on to the next part, okay, we have this right here, right? Your nickel 2 plus cation. Not difficult at all. Just be careful. You remove 4s first, then remove 3d. Okay? Okay, going over to part 3. Okay, part 3 is where we talk about d orbital splitting. We talk about crystal field theory. Okay, we talked about this before actually, so you should have a slight advantage in this question. Okay, I hope you all realize, right? The square planar, we have done a question before where they told you guys how square planar orbitals are being split. Okay, take note, right? You only need to know octahedral and tetrahedral. Okay, and you should know how the ligands approach. But as for square planar, you are not required to know. So how this question actually tests you guys, right, is they actually give you guys what is the most highly splitted orbital. Okay, the highest energy level orbital, right, is the one that receives the most repulsions or least repulsions. The most repulsions, yes. Okay, so in other words, you can actually work backwards from there, right? But we actually talked about this before also. We mentioned that in a square planar complex, right, how do the ligands approach? Can you remember? Okay, or based from the inference in this question, right? If this guy is a higher splitter orbital, that means the ligands they approach along the what axis? Okay, so if you just say along the axis, right, it's not enough. Okay, so guys, when you say ligands approach the axis, it implies ligands approaching from all axes. All axis is for octahedral shape, but for square planar shape, right, it only specifically approaches along the x and y axis, which coincides directly with your x square, y square. Okay, so you must tell me that as well, right, in the first part of your question. Okay, ligands approach the central nickel 2+ ion from or along the x and y axis. Yes. Yeah, okay. I sent her the link already. Okay, so if you approach along the x and y axis, okay, then the next thing is you must tell me how they interact with the ligands, right? So you can tell me that this will cause, or wait, okay, in a dx square y square ligand or orbital, okay, how are the electrons, how is the electron density located? Okay, it's also the same thing, right? That's why it has the highest energy level. Okay, in a dx square y square orbital, the electron density is concentrated along the x and y axis. So you can see, right? Okay, since the electron density is in the same plane as how the ligands are approaching, then it's going to result in very large amounts of repulsions. Okay, so you can just say it faces large amounts of repulsions, and that's why it's split to the highest energy level. So we have talked about d orbital splitting quite a number of times already. Okay, as if your electron density is in the same plane as how the ligands approach, right, it's gonna face a lot of repulsions. But if they are in different planes, right, then it's not gonna face as much repulsions, and then you're gonna have a lower energy level. If you look at the diagram for this question, they ask you guys to draw the orbitals, right? Dx square y square, you just need to lie along the x and the y axis. So that's how this question looks like, correct? Okay, but then of course, you need to relate it to how the square planar complex, the ligands are being approached. Okay, square planar ligands approach only specifically along these two axes. So I think it's good to know this, right? Okay, because number one, we talked about it before, and number two, right, if this does come out, at least you know in advance, right, how the ligands are approaching. Okay, so just bear in mind, right? Any questions so far? Okay, I want to now talk about part 4 and part 5, actually, part 5 to be specific, because part 5 explanation requires a bit more to write. Okay, but first let's look at part 4, right? Part 4, they are talking about unpaired and paired electrons. Okay, so okay, later on we copy up. Okay, so look at part 4 first. They talk about paramagnetism. Now, guys, paramagnetism has been discussed before. Now they just reintroduce the idea. If you have unpaired electrons, you are paramagnetic. And they say that G is paramagnetic and not F. Okay, so we look at G first. It has unpaired electrons. Now there's 3d8, 8 electrons. Okay, again, if you follow your rules first, if you pair them singly, then you pair them double later. Okay, and you always go from lower orbital to higher orbital. So I've gone from lower to higher, and then I fill up from lower to higher again. Then those are my 8 electrons. Can you see that? I think this is quite straightforward because it follows whatever that we have learned so far. There are unpaired electrons, so G is paramagnetic. Okay, but guys, this F, right, also has 8 valence electrons. But how are you supposed to position the 8 electrons on the square planar? Okay, if you do the same thing, right, lower to higher, single then double, you will end up with something like this. And is this correct? No, right, because they are paired electrons. So what you need to do is actually bring one of these electrons, right, down here. Basically, what you need to do is to pair all the 8 electrons. So 2, 4, 6, 8 lah. Okay, that's how you pair them. And you must pair from the lower to the higher level orbitals. Okay, so some of you guys may be asking me, why do you leave the highest orbital empty? Right? Okay, so remember, guys, in the table, they mentioned that F and G have respective colors. In order to have colors, the electrons must do what first? they must promote to a higher energy level, right? And to promote to a higher energy level, it implies that the energy level on top must be vacant, right? Because only if it's vacant, then it can accept the promotion of the d electron. And it works for tetrahedral as well, because even though these are not vacant, right, there's at least space for an electron from the bottom to promote to the top. Same idea over here, you need the top to be empty so that it can promote to the higher level also. If the highest level over here is occupied, then you're not going to see any colors. Make sense? Yeah, so just be aware of the idea. So just fill up from the lower to higher energy level. That's the principle behind it. Yes.
Basically, I just like put the one up. So I put every single.
No, the thing is now, right, you have unpaired electrons. But we cannot have unpaired electrons in F because they say F is not paramagnetic. In order to be paramagnetic, you need to have unpaired electrons. If it's not paramagnetic, means no unpaired electrons, meaning everything is paired. Makes sense, right? Yeah, okay. Let's move on to part 5, right? Part 5, we need to explain colors. Okay, let's just do a quick recap. Whenever we look at colors, right, what are we actually looking out for? Okay, our syllabus actually taught us 2 different factors. Okay, but then let's look at it first. The first factor is different oxidation states. Okay, if you have different oxidation states, it will interact with the ligands differently, right? Okay, because different oxidation states got different number of p electrons. Okay, the next thing is the different one. Okay, so your different ligands first. Okay, this one is very important because different types of ligands will approach and split differently. Okay, but the idea is, if you look at this question, can we use any of these factors? No, okay, because the fundamental idea in this question is that they have the same oxidation state, same number of and same types of ligands. It's actually the shape that's different. So perhaps you can add on, right, a third factor, right, to this shape question. To this color question. Why do they have different colors? Because they have different shapes. What do different shapes even mean? How does it lead to different colors? So you need to slowly break it down. Okay, what does it mean to have different shapes? Okay, before we get to different extent, okay, let's build everything slowly. Don't leave any stones unturned. Okay, so over here, you must have different approaches. Okay, the ligands will approach differently. So let's just talk about that. Okay, different shapes, ligands approach the central ion differently. Or you can say from different directions also, okay. Now, if you approach the central ion differently, then it's going to split to a different extent, right? As you can clearly see. So you can tell me that the d orbitals split differently. And when it split differently, then what happens next? Okay, let's slowly path our way to the answer. Okay, what does it mean to have split the d orbitals differently? What's the next idea we need to talk about? Different energy gap. Okay, so you need to tell me that also. Okay, it results in a different energy gap, which is your delta E. Okay, but this is where a lot of you guys will stop your answer. And I don't, let's be safe over here, right? This may not be enough to get you your full marks. Okay, especially if they start awarding 3 marks for this question. Entirely possible. Okay, the next idea that I want you guys to introduce into your answer again, right, is how delta E links to color. Can you remember a formula, right, a relationship between delta E and something about the light color? Okay, good. So your delta E, right, is actually inversely proportional to your wavelength. Just introduce this into your answer, then you can tell me, right? Okay, with a different energy gap, the wavelength of the color or the wavelength of the light absorbed is also different. Now take note, guys, there's a very important idea over here just to make sure. This expression, the lambda, is it the color absorbed or the color observed? Okay, take note, it is the color absorbed. Okay, the color observed cannot be determined from this value of lambda because we talked about the idea of complementary colors. So to end off your answer, a different color absorbed will also result in a different complementary color observed. So that's how you path your way all the way to the end, right? Why you observe different colors. Okay, it's because of all these little things here and there. Okay, so that's how you explain color questions in general. Yes.
To explain that G has lesser delta E.
Okay, that part you don't need to know to explain because when they say different colors here, right, your job over here is really to bring out the fact that the main difference, the root cause lies in the fact that their colors are different. They have different energy gaps between. We are not expected to specify why you see red and why you see green. Okay, I think those are the two colors they've given us now. Okay, red and green, right? In order to justify, right? Okay, it's a lot harder. Okay, because here, right? Okay, we don't actually know which energy gap is larger, which energy gap is smaller. Okay, they never specify anything about that. So this is more or less a more generic question. Okay, but if they want you to specify and justify why there's red and green specifically, they would say so in the question. Why does this guy have a red color? Why does this guy have a green color? Then you go ahead and explain why a higher energy gap, smaller, whatever color. Okay, then you talk about this in greater detail. Okay, but here they just ask why they have different colors. Okay, so talk about it in a more generic manner. Okay, that's the answer to this question. Okay, Ken? Okay, and then with that said, right, okay, we can also talk about the final part, which you guys have drawn. Okay, they talk about the cis isomer, which I think this is quite okay. Now take note, for square planar, the bonds that are facing away, right, should be pointing inwards. The bonds that are facing yourself, right, should be pointing outwards. So you cannot change the wedges. Okay, don't go and flip the wedges. You should maintain the wedges and then just change the groups. So over here, right, I'm just going to put my CL on the same sides. Okay, and then this should be your answer. Okay, this is your cis isomer. But the follow-up question is this. Okay, you need to look at the structure very carefully. They are saying that this guy is not favored, but this guy is favored. So any idea why? We need to explain why the cis isomer is not favored. Okay, steric hindrance. Okay, that's the only answer. Okay, generally, cis isomers, the groups are on the same side. But guys, if you just write steric hindrance, it's not enough. What aspect of steric hindrance? Like you take a look at this question here. Is it the CL? Then they're on the same side, what? But is that steric hindrance? You should be talking about the more significant ones, which are this group over here. Okay, this group over here, right? If you forget how it looks like, just going to refer back to the first page. They told us why exactly this guy is. Okay, you need to explain in greater detail. Why is he sterically hindered? Why you don't talk about chlorine here? Why does this PPH3 cause more steric hindrance? Okay, larger molecular size is one thing, but you go and look at the structure, right? What exactly makes it very bulky and very sterically hindered? It has multiple benzene rings. Okay, it's already by itself super bulky. So in other words, if you put them on the same side, it's gonna enhance the effect. Okay, and that's not what we want. Okay, so in other words, okay, to explain this question, you must first tell me that the PPH3, okay, groups are very bulky. So that's one. You justify why it's bulky, as it contains multiple benzene rings. Okay, then since they are on the same side of the nickel ion, okay, there's large amounts of steric hindrance. So you notice how I explain this question, right? I try to keep it as short and concise as possible, but at the same time, I try to include as much detail as I can. I justify why it's bulky, because there are multiple benzenes. And then you also tell me that why cis in particular is because they're on the same sides. That's why there's a lot of steric hindrance. And the answer isn't very long, right? Okay, it's perfect for 1 mark also. Can you see that? Okay. So overall, I think this question doable. Okay, it's just very conceptual. Need to write a little bit more, right? But yeah, that's pretty much it for this. Okay, we don't have time for part B over here. Okay, so I just want to move on to another question really after this. Yes.
Steric hindrance strains only.
Steric hindrance, yeah, same thing. Hindrance, strain, both okay. Someone hear the word steric inside. Okay, for those who are okay, right? Okay, take a look at question 2. Okay, for question 2, I think this is a good question. We're going to try most of the question for today. Okay, but I want you guys to start with part A. Okay, part A is something that we've done a couple of lessons back. And I just want to see whether you guys can remember how to justify this question. Okay, so I'm only going to give you guys 5 minutes for question 2A, right? Aromaticity. Yes, they give you criteria to fulfill also. Okay, so just go and explain that. A2A. Okay, we have about 3 minutes left. Bye. No, because you never thought about it. Yeah, you never thought about why this guy in particular. Because when this is only enough if they ask for aromatic compounds in general. But now they're talking about this compound. Like you need to give me a more contextualized answer, like why this compound has that. Like why is the what's this compound a particular staple? What does it have in its staple? So we talk about it briefly. And how that normal sentence is enough. Just 30 seconds left. Okay, time's up. Right, okay, let's take a look at the two parts here. Okay, just to again reinforce this concept. Okay, but there's a few things that I want to talk about also, additional things. So take note. Right, okay, so first of all, right, we are supposed to justify why this guy is aromatic. Now let's look at the first criteria. So it must fulfill the first criteria. All carbons have p orbitals. How do we justify this? I mean, we can't just write this statement again in our answer, right? Because it will just seem like you're just copying from the question. Okay, so how do we justify this first part? Why do they all have p orbitals? Yes, okay, so they even clued us in with the word hybridization. You must first tell me that all the carbon atoms are sp2 hybridized, and that's why they all have an unhybridized p orbital each. Okay, thus they have a p orbital each. Okay, so that's the first part. Okay, again, for these kind of criteria questions, you want to make sure you don't just end up paraphrasing and copying the question. Okay, so if they have a p orbital each, then next you can tell me about their continuous overlap. Okay, why can they overlap continuously? It's because it's a cyclic structure, right? Okay, so you can briefly mention that as well. Okay, so hence they overlap in a continuous fashion. Okay, this part over here is not value adding because you're just copying the question. Okay, give me a reason why. Okay, as it is cyclic. Okay, so it's because of that, then it allows for continuous overlaps. Now, I just want to point out one thing. Okay, so this is where I'll talk about this. This carbon over here is sp2 hybridized. Now, based on our knowledge of hybridization, right, we wouldn't have known that this carbon is sp2 hybridized. Because I told you guys about how we count electron regions. 4 electron regions, sp3 hybridized. 3 electron regions, sp2, 2 electron regions, sp, correct? Okay, and we take a look at this carbon in particular. So let's digress a little bit. Okay, you guys have seen carbocations before. Carbocations have 3 bonds and a positive charge, correct? What hybridization is this carbon here? sp2 because there are 3 electron regions, right? Okay, so that's fine. This one's okay. But you guys have never really learned carbo anions before. Okay, so let's take a look, right? A carbo anion also has 3 bonds, but yet now this guy has a negative charge. So what else does it have? Okay, 3 bonds, positive charge. Okay, makes sense. Then how come have 3 bonds, negative charge also? What else must the carbon have? Lone pair. Yes, good. Okay, so it's rich, so it must have a lone pair of electrons. And now you look at the number of electron regions, right? By right, what's its hybridization? Based on our knowledge of electron regions. How many was this? Yes, sp3, right? Okay, because there are 4 electron regions. By right, it's supposed to be sp3. But based on the question we have been given, right, this guy is actually sp2. And let's just identify one thing, right? And this is actually necessary for the next part of the question. Okay, remember, guys, for sp2 hybridization, we have 3 sp2 and 1 p. sp2 hybridized orbitals, how do they overlap? Okay, sp2 overlaps head on to form sigma bonds, right? Okay, so let's just count all the sigma bonds up. One sigma bond uses sp2, this guy also uses sp2, this guy finally also uses the last sp2 hybridized orbital. So all the 3 sp2 used up already. Okay, then how about p orbital? P orbital is used to form what kind of bonds? P orbital overlaps to form pi bonds, right? Okay, but are there any pi bonds in this structure? There are no pi bonds. Okay, so what does that mean? The p orbital is free, right? Okay, he's free to do what? Okay, he's free to actually house this lone pair of electrons on carbon. So in other words, the lone pair of electrons on this carbon here is actually in the p orbital. And that it will talk, that part, right, will actually contribute for part 2 also. How many pi electrons are there for the second criteria? This compound, how many pi electrons are there? Okay, it could be 6, not 4. If it's 4, it wouldn't fulfill the criteria as well, right? It's actually 6 pi electrons. So what's the value that you're adding to this question? you're supposed to break down where these 6 pi electrons come from. So there are 6 pi electrons, 4 of which come from the pi bonds, right? Okay, so we talk about that also. Okay, 4 pi electrons come from the 2 pi bonds. And then your final thing is to tell me where the last 2 pi electrons come from. They come from the lone pair. Okay, so we talked about this in the other question in the previous lessons as well, right? If the lone pair contributes to the delocalized pi electron cloud because he's in the p orbital. So that's what you can tell me as well. Okay, and the lone pair of electrons on the negatively charged carbon is in the p orbital. Remember, overlapping p orbitals results in delocalization. So now this lone pair can delocalize. So just give me a reason behind that. Hence, the lone pair of electrons will contribute to the delocalized pi electron cloud. Can you see that? So at the end of the day, right, that's your value that you're adding to the question. You are not just paraphrasing the question and then just telling me, oh, there are 6 pi electrons. Where the hell did the 6 pi electrons come from? You must then give me that explanation, justify it. But the main justification here, right, is about the lone pair. It's actually the p orbital. That's why it can contribute to the delocalized pi electron cloud. So you must have these keywords in your answer. Last but not least, you can just bring in your 4n plus 2 formula, right? So 4 times 1 plus 2 give me 6 pi electrons. You can add that in also, but you probably not give you much credit lah. Okay, the credit comes in with the red color words and your 6 pi electrons lah, basically. Okay with this? Yeah, okay, so this second part over here not as easy to explain as you can see, right? What do you mean don't care? You must care. It's in the pure. Okay, I'll come to that right now. Okay, after this. Okay, so yeah, you are asking me, right, when does it become sp2? Okay, by right from our electron region rule, right, this should have been sp3. Then how do you know when it's sp2? Now, number one, you don't have to worry about this too much, but I'll still tell you guys how to determine. Okay, why you don't have to worry is because the question will clue you in as to why it's sp2. We know this was sp2 because of criteria 1. Criteria 1 is fulfilled because he has a p orbital, meaning he's sp2 hybridized. So that's how I know he's sp2 hybridized. But to give you guys a bit of additional information, that's why I drew out these 2 other structures as well. When does it not follow our electron region rule and then end up as sp2 hybridized? These are 2 more examples we have gone through in the past. Amides are a classic example. How many electron regions are there on nitrogen in the amide? 4, right? Okay, 1 lone pair and then 3 sigma bonds. 4 electron regions by right should be sp3, but it's actually sp2. Similarly to this guy, Pyro, 4 electron regions, yet he's also sp2. When does this happen? So additional advanced information for you guys is whenever the atom, right, is adjacent to a pi bond, it will rehybridize into sp2. Okay, so you can possibly write this down as well, right? If it is adjacent to a pi bond, there is this concept that's not in your syllabus, it will rehybridize into sp2. Basically what it means by rehybridize, right, is that initially it is sp3, that's correct. But because it's beside a pi bond, it will actually undergo one more round of hybridization and turn it into sp2. You guys don't need to know why, like something to do with more effective overlaps and stuff. Okay, again, that one not important. You see, right, beside a pi bond. This one also beside a pi bond. This one also beside a pi bond. Okay, so in these 3 examples, that's what I mean by adjacent to a pi bond lah. Okay, again, you don't need to know this because the question will definitely clue you in that. But just additional information. Okay? If there are no questions there, I'll talk about part 2 very fast. Okay, for part 2, they're asking us, right, okay, about your substitution and addition. Okay, a lot of you guys will just write this. Substitution will preserve stability. Addition will disrupt stability. Okay, this is only enough, right, if they're asking for generic aromatic compounds. But this isn't a generic compound. They specifically drew out a guy called naphthalene, right? Okay. So your standard template answer here, right, is not enough. Okay, you just tell me this is actually not enough. You need to give me in context. Guys, naphthalene, why is he stable in the first place? Where did this extra stability come from? Why does naphthalene? Okay, because of resonance stability. Yes, okay, you must tell me why also. It's because of his delocalized high electron cloud. Yes, okay, so just give me your answer in context of the question. So next time, right, okay, the trick is this. Whenever they ask you guys to explain a particular structure, you must make reference to the structure. Attempt to make reference to it. Okay, at least they will see your effort in doing so. Okay, don't just give me a template answer here. Okay, so naphthalene has a delocalized high electron cloud or high electron system, which gives it extra stability. You can say extra or resonance. Again, these are additional stability to the compound. If then you can tell me that substitution must preserve it, addition will disrupt it, which is not favorable. Okay, then that's the final answer. All good with this? Okay, so we have done this question before. Okay, the only tricky part to this is your part 2. Okay, A criteria 2. Okay, if there are no questions here, let's just quickly proceed. Okay, those who are done, we can start off with the next page already. I want you guys to do part B and part C. I'll give you guys time for this. Okay, there is space on the next page for working. Okay, so you can write it there. Yes. Okay, this one, right, again, is not something you need to keep in mind because we are not taught on this in our syllabus. Don't worry, for this kind of questions, right, it is pretty much assumed to be evidence. Okay, let's just say, right, they ask you to compare basicity of 2 nitrogen compounds. You should assume it has sp2. Again, the assumption is not very clear. That's why I give you guys this information. For this question, we know this is sp2 because it has a p orbital. So that's how we know it's sp2. So you don't need to really know about this adjacent to pi bond thing. You see, right? Okay, they will give you a clue in the question to tell you there's sp2. Okay, this guy, they gave us, okay, the question that we did regarding this compound, right? They told you it's sp2 already. Like straight up, they typed it out. It's sp2 hybridized. So don't need to worry. Okay, amide is the only exception, right? It's amide. Amide, you must know it's sp2. The rest, they'll tell you. Okay, they will tell you here, this one is inferred. Okay, from the question just now, you infer.
Yep.
sp3 is no p orbital, yes. Okay, just begin on your part B and part C. Okay, just where I'm working on the next page. Okay, so this one about 6 marks only. Okay, I'll give you guys 9 minutes for this. Okay. Okay, do your part B and part C. You smell it, open the door. This kind of gets sick of it. It's 6 minutes there. Who compiled the Uh, it is 2320. Okay, one last minute. No, it's not about 201. It is, but it's not about 201. It's just delocalization. Resonance is about delocalization, but then you're reasoning about how oxygen got 2, nitrogen got 1. That's not. We never look at the number of loop pairs. The number of loop pairs doesn't determine how strong your resonance effect is. It's more about the extent of the delocalization. That's up to you. Neither. Yeah, give you guys a bit more time. Okay, we have 30 seconds left. Okay, I'm going to stop the time there. Okay, let's go over the mechanism first. Okay, quite a few things that I want to discuss, especially for a simple part like part 3, right? There's actually a lot of things to talk about. Okay, so first of all, I want you guys to take a look at the mechanism, right? For part 1, right, okay, they said SO3 reacts with H2SO4 to produce one of the electrophiles, right, which is this guy over here. So all you need to do is to go and balance. Okay, the other species here has to be HSO4 minus, right? Okay, because you're just transferring one proton from H2SO4 to SO3. Okay, and then the next thing is also, right, this is an acid-base reaction. Can see that? Okay, because it's a transfer of proton. Okay, and acid-base reactions, I tell you guys to use what arrow? Full arrow. Okay, so if you roll a full arrow, okay, good, that's correct. Okay, but then in actuality, right, this reaction kind of sucks. So it's a reversible arrow lah. Okay, so the answer key is reversible, but I don't expect you guys to write reversible. No. Okay, because if you follow my principles of if you follow my principles of acid reacting with base is full arrow, right? I think it's still correct. Okay, I'm not gonna let's not change that. Okay, so I think this is fine also. Okay, so let's stick to that. Okay, the next thing is the mechanism, and there are a few things that I want to address, right? Mechanism, I told you guys from the start, it's all about following instructions. Just follow instructions, meaning to say, if this is your final compound, you do whatever it takes to get this final compound. So why do I mention this? Is because, right, some of you guys tell me benzene is rich, oxygen is poor, so rich will attack the oxygen. Now, it's entirely possible for the benzene to attack oxygen, yes. But it just doesn't happen in this mechanism. Because in this mechanism, benzene is seen to attack sulfur. They are bonded to sulfur, so you should be attacking sulfur instead. Even though sulfur doesn't look poor, right, compared to oxygen, you just attack sulfur because that's eventually what is bonded to. So don't just follow the ideas of rich attacking poor blindly. Okay, sometimes following blindly will not give you your correct answer. Okay, so follow by looking at the final product. Okay, then of course, when they attack sulfur, what will happen next? Sulfur has 6 bonds currently, which is the maximum, and then now you form a 7th bond. What's going to happen? Okay, something needs to break, and then that's when it breaks and then fulfills the oxygen's positive charge. You can see that? Okay, so that's the arrow movement for this question. And the last thing that you need to take note of is also this. It's substituted onto the 4th position, so your ring must be broken towards the 4th position. And also that means your arrow must originate from the 4th position as well. A lot of us, right, out of habit, you originate from this portion over here. But that's wrong. You're opening up the 2nd position already if you do that. Okay, I want to use the 4th position. So you just do that and then you bond to your sulfur. Oxygen now no longer has a positive charge and it only has a single bond. Right? Okay, and then that's your intermediate. Okay, don't forget your CH3 as well. Okay, this right. Okay, you can add your slow step as well because electro sub first step is a slow one. You're disrupting the aromaticity. And that is slow. Okay, can? Okay, you repeat the same thing, right? Okay, just take out you just bring out your intermediate once more. Okay, and I forgot one more thing. I want you guys to mention the H. The H is still there in the intermediate. You want to draw it out also, right? Because you will have to show the electron movements over here. As you can see, this hydrogen needs to go, right? Okay. And once it goes, the electrons must be used to repair the ring. So you point it back into the ring here, as you can see. Okay, can? And once you have done this, you must also ask yourself, there's something that needs to get rid of H. What is the thing that gets rid of H? Your HSO4 minus, right? Okay, because how do you know is this? Okay, it's a negative charge, yes, and at the end of the day, they say that H2SO4 is regenerated, right? So remember, guys, I want your lone pair to be an oxygen. The lone pair is not on sulfur. Okay, that's a common misconception. Okay, then you use it to attack the H, then the electrons will break and go and repair the ring. Okay, so now the ring is repaired, the H is gone, and then you get H2SO4 regenerated. Mechanism-wise, I don't think this is difficult, right? They just introduce a slightly different electrophile. But apart from that, everything else is the same if you realize. Okay, you don't need the title because the title has been given in the question already. You read it, also won't get bounced up. All good with this? Can I? Okay, I want to use this, right, to also talk about part 3. Part 3 seems easy, right? Okay, but there's a few things to discuss also. Okay, the entirety of this question, I feel that is very important. Okay, now for part 3, right? Okay, you can first of all, part 2, any questions? Anything you all want to clarify from your answers? Yeah, okay, can you look at part 3, right? Okay, what's the reagents and conditions? Or just tell me what are the reagents first. Okay, and corn H2SO4. Okay, good. Okay, but the final thing that I'm here to discuss, right, is your conditions. Okay, your conditions for electro sub, right, got 3 conditions. Okay, the normal one is warm, right? The milder one is room temperature. The stronger one is heat. You have 3 different categories. Now, looking at these 3, right? Okay, again, it depends on your substituent effects. Now, guys, you look at this guy, this substituent. This is what? This substituent is alkyl group, which is activating, right? Okay, it is electron donating, so it is activating. So if it activates the benzene, do you require milder or stronger conditions? Milder. Okay, so milder means room temperature, right? But then you must also account for the fact that I have another substituent on the benzene. Now, this substituent cannot be found from the data booklet. So this is something important. I want you guys to infer. Do you think this is donating or withdrawing? It's one or the other, right? Okay, how do you know it's withdrawing? That's correct. Okay, good. O is more electronegative than S. So you can see that these are polar bonds pointing away from the benzene ring. You can see that. So it's the electron withdrawing effect. There's another way to tell that it's not donating. In order for it to be donating, the atom bonded to benzene must have what? It should have a lone pair, right? Because with a lone pair, then it can delocalize into benzene, so it's kind of like donating. The only exception to the donating rule is alkyl groups. Alkyl groups are just donating, you don't need to know why. Right? Okay, I know it doesn't have a lone pair, right? But alkyl groups are just donating full stop. Okay, but for the rest, okay, there's a lot of other things, right? With lone pairs, quite likely it will delocalize on. But there's no lone pair. At the moment there's no lone pair, right? Like for example, NO2. This N over here, right, has no lone pair, so it's already considered withdrawing. Can you see that? Now the issue is, now what's our conditions? We have one donating and one withdrawing, right? So it kind of like cancels each other out, right? Okay, so what's the condition we can use here? Okay, wait, we don't use numbers yet. It's either room temperature, warm, or heat. 3 categories. Okay, what should we use here? Okay, you can use warm, because warm is in the middle of mild and strong, right? Okay, so warm works. Okay, but the answer key also accepted another one, which is heat. Okay, because guys, you try to avoid anything below warm. Don't write room temperature. Because our room temperature is only if there is a donating group. But now that you introduce a withdrawing group, right, room temperature may not be enough. And that's the last thing that you want to happen. You want to make sure that it can react. Heat is a bit more safe because at least you can some sort guarantee the reaction. Higher chance to guarantee the reaction. Now D-sub, is it? Yes, okay, but it's okay. That's why I say warm is the best. Okay, warm over here is in the middle ground of both activating and deactivating. Again, we don't know this guy how strong or not. Okay, so we don't know whether donating or withdrawing will outweigh one another or not. So we treat it as if they neutralize each other. Okay, so we just choose the middle ground temperature, which is warm. Okay, and your heat, right? Okay, if you put too high, right, then of course you might end up in multi substitution lah. So if you want to write numbers, right, warm is 55, room temperature is like 30 or something, right? Okay, heat, right? You try to just boost it up to 60 degrees. Okay, just don't put something too ridiculous. If you put like 100, right, definitely will have multi-sub one. Okay, and you don't want that to happen. Okay, this. Right, okay, so the conditions wise, okay, activating effects, deactivating, okay, quite important. Okay, and that brings us to part C actually. Okay, part C is also directing. Yes. You want to write warm and heat also, okay. Yeah, numbers if you want also can. Yeah, okay, both are acceptable. Okay, this is where I want to discuss part C. Very important question. Okay, we don't see this that often, right? Okay, but if it does come out, I want you guys to score for this. Right? Any questions so far? Okay.
The actual donating and the deactivating is like just like how you determine the
What? Yeah, one will boost the guy, the other one will make it harder to react. So it cancels out. Room temperature, warm, heat. So the middle ground is like the safest. Right, yeah. Okay, guys, come. Let's look at part C. Okay, you have any questions here? Okay. Okay, how do you answer part C? Part C says B is preferred over the C. First of all, I think you want to always ask yourself, comparing two compounds, what's the difference between these two compounds? Can someone tell me what's the difference here? Huh? Okay, the position of the PR. Okay, why is the position of the PR different then? Is it random or what? Is there a rhyme or reason to why they are different? It's because of directing effects. Yeah. Okay, so directing effects is the reason why they are different positions. Now for structure B, right, with whose directing effect am I following? Okay, NH2. Okay, now first of all, NH2 and OH are the OGs in the benzene ring, right? So you must either follow OH or NH2's directing effect. And if you don't know what the directing effect is, your data booklet is your best friend, right? Okay, they already have it there. Both are 2,4 directing. So can you see, right? Okay, this guy follows NH2's 2,4 directing effect. This guy follows OH 2,4 directing effect. Can you see that? Then how? Then what's the problem over here? B is preferred to C. What does that mean? Yes, NH2's directing effect is who you follow, right? It is more significant in that sense. So let's answer our question backwards. If B is preferred to C, it implies that NH2's 2,4 directing effect is more significant. Okay? So remember, I want you all to know that the main idea behind this question is that directing effects are a competition. You must always follow whose directing effect? The stronger one, yes. The more activating substituent is the directing effect that you follow. So if now I'm following NH2's directing effect, what could that imply? NH2 is more, you shouldn't use the word stronger. We don't describe substituents as strong or weak. They are more activating or deactivating. Yes. Okay. So in this case, if you follow NH2, means NH2 is more activating than OH. Now, both of them are under the same category. It's not like one is activating, the other is deactivating. They are both activating, right? So it's just that this guy is more activating than the other. But why is that so? How are they activating in the first place? Okay, they are both activating via resonance, right? Okay, as you can clearly see here, they both have lone pairs. This guy lone pair delocalized. This guy lone pair also delocalized. Then what's next? If NH2 is more activating means what? How do we discuss? What exactly makes it more activating? Delocalize more lah, right? Okay, so NH2 must delocalize more than OH. Tell me that. Okay, so the lone pair of electrons on nitrogen delocalizes into benzene to a larger extent. Okay, then the lone pair of electrons on oxygen. Can you see that? And then finally, we boil it down to the root cause. Why exactly does it have more delocalization? Why does it have a greater extent of delocalization? The lone pair can go into the benzene more easily. What does that mean? Why is that so? What's the difference here? Electronegativity, right? Okay, a lot of our reasoning is tied to N versus O1. Okay, and if you realize, okay, if N is less electronegative than O, what does that mean? Okay. More readily delocalized, yes, okay, but we mentioned that there already. So you can say something like N holds onto its lone pair less tightly. So if it holds less tightly, that means it's more willing to give it to the benzene, right? Okay, and that's why we talk about delocalizing the benzene to a greater extent. And you slowly build your way back up. Okay, so my arrows over here follow my thought process. You should be working from the answer they've given us and backwards. Trace it all the way to the root cause. That's what it should be happening in your head. And then what you should be writing down is start from the beginning and then write towards your answer. Okay? Sometimes these kind of questions will warrant this kind of thinking. Okay, so I need you guys to try to follow this. Right? Who will start next to this question? It's not just about answering techniques. It's also a good learning point. Directing effect is a competition. Always follow the more activating group. Okay? I know sometimes, right, 2, 4 directing, 3 directing can point to the same position. Yes, that's a rare case. Okay, then that one will reinforce each other. But other than that, most of the time they will when they conflict with each other, right? Like this case, then it is a competition. Okay, all good with this? Right? Okay, so I think it's a good question in general. Okay, and with that said, we try one short part before we take a break. Okay? Inductive. That one just bases off your polarities. So like this is more electronegative, so it's polar. Yes, okay, because this guy no delocalization. Alkyl is just inductively electron donating.
Oh,
no delocalization.
same for halogen.
Halogen is also delocalizing, right? Okay, but halogen is another problem now. Okay, if you all look at your data booklet, right, your halogen is actually what effect? Deactivating, right? Okay, why is it deactivating? Does it have a lone pair first? Yes. Now, halogen has a lone pair, so it can delocalize, right? Okay, so based on the resonance effect, it is donating or withdrawing? Donating, okay, we just settled already, right? Okay, but there's also everything here, all the substituents has another effect also, inductive. Inductive effect is, as you can see here, Cl is more polar than carbon, right? So it is going away from the benzene, it is actually withdrawing. But at the end of the day, right, if it's actually deactivating, what does that mean? Whose effect is stronger? The inductive effect is stronger than the resonance effect. As to why inductive is more significant, you don't need to know. But this is what you can infer lah. For halogens, inductive ends up stronger than resonance. For OH, I can just go through phenol also. Okay, let's do the same thing. Resonance effect is what? Donating or withdrawing? Donating. Because it has a lone pair, it can delocalize into benzene. Inductive is what? Withdrawing, because O is more electronegative than carbon. It is the same thing, right? But yet, at the end of the day, what is it? It is donating, right? Meaning to say, what can you infer from that? Okay, if it's at the end of the day is activating, it means its resonance effect has to be more significant than the inductive effect. As to why, again, you don't need to know already. Okay, I can explain that, but it's going to confuse you guys even more. Mesomeric is only in your EJ notes, that one not tested. Yeah. So barely know what it means. don't need. If I don't know means you don't need. Yeah, okay, legit. That one I saw in your notes before. I think I saw you passed me your notes that time I saw. Yeah, okay. I have no idea what that is, and it doesn't matter. Yeah. I have no idea. You ask me frankly, I have no clue what that means. Okay, and it doesn't matter. Okay, you don't need it. That's what I'm trying to say. Okay, ignore that word. Okay, it's probably legit. Yes, your teacher isn't wrong, but teacher doesn't know what you're doing. Okay, they don't understand that you don't need to understand that. Okay, I don't know what mesomery is, serious, and I don't care. You tell me, I also don't care because it doesn't matter. Okay, so guys, once that's done, can you guys take a look at part D?
But explain it last one.
Yeah lah. What do you mean explain?
Is the resonance?
Yeah, same thing. Okay, doesn't matter. Use the word resonance lah. Resonance much easier. What the hell is mesomeric? Okay, come. Take a look at part D. It's just drawing of a few structures. Then we are gonna take a break. Yeah, after this, right? Come. D is important. D is important. Let's go. Yeah, D part 1, D part 2. Okay, this one will give you guys like 6 minutes lah. Okay.
I saw the
What? Yep.
When you sub like that, right, is it roaming yes or must you use CPL? That one not even tested. Yeah,
You're talking about step 1 or 2?
Step 1.
Oh.
Not tested. Tested.
Yeah, PR2 lah. Cannot be HBR because HBR, right, will only substitute you add 1 H, 1 PR. But you want PR2. So PR2 in CCl4. Yeah, that's the answer. PR2 doesn't exist as a gas. It's either that or PR2 liquid. Both are acceptable.
But not PR2 liquid can also. So they give you PR.
No, that's a
These
two are the same thing. You can just use all room temperature. Addition is all room temperature for alkenes because the pi bond very easy. So room temperature is enough. Because I never write. The degree doesn't matter. It's more a relationship.
You look there for no, what way? That is my formal. I'm not formal, but like what's it called? It's called smart casual. Smart casual. So smart and so fun.
One speech. Icebreaker is it the sour? Is it? Is it the? What is another one called warheads? Yeah. They're not Singapore, I think.
不会，你 access
芒果
都是 cat，
也是，你都是 specify confused。
我就说不让这个话。
哎呦，
也开个。
You're in Korea in early December, right?
I'm going the basic.
Going in the end of going with them. Yeah, I'm going with them. In Korea, nice well, lucky you change from
What would you do? I don't know. Going to.
drinks going through the whole year.
What's the power of the?
I just go there and drink only.
No, that's good.
Oh, it's quite good.
Oh, so this is what you.
I like that barbecue. You guys don't get carried away after in levels and snap you guys back to reality. Okay, come on, 2 questions first. Need to break after this, break after this. I know the soul incident, right? Man, I won't die on. What's 150 in a scale of 7 billion people on Earth? Okay,
The chance rate of you dying there is 0.1.
okay, I realized our life actually very fortunate to be in Singapore because I saw one video recently, right? You know, Iran now got a lot of issues, right? You have to know GP, right? Okay, Iran now have a lot of protests for the women and all that. The police just shooting all the women, right? It's true, like you saw the video, right? This woman in a car, just driving a car slowly across the crowd. Then there's she's just taking a video of like the police. They hear gunshots already. They boom, boom, boom. Then they're like, oh shit, what are they doing? What are they doing? Suddenly the camera, right, just dropped, right? Then got blood spill. It's because the woman taking the video got shot.
Oh, I love you.
Out of nowhere, she just got shot. She's in a car, just driving only, never do anything with the police. Just got shot. I see already, I'm like, oh my god. Imagine living there. You just die for no reason. Yeah, what the hell, man? Cannot. That's why last time I said I want to go Iran. Serious, before all this went down, right? I was like, as a woman, as a guy, it's fine. As a woman, don't go there. Because as a guy, right, you go Iran, they say it's very nice. The people are very nice also. Just the police are big issues. The government also got issues.
What was it in Iran?
Red Sea, I think. I think that's what it's called. It's like the sand is like yellow, right? No, not the Red Sea. It's the sand is red color. And then they have this ocean where there's so much salt concentration, right? The point we can float on. I think it's there, if I'm not wrong. The concentration of salt is so high to the point where you're less dense than the water, then you start floating. To like submerge in the minerals, right? Yeah, right. Hey, can I go through the okay, faster draw your compounds. 3 compounds to draw. Part D only, part D only. D part 1 is just conditions. Okay, D part 2 is your whatever.
Yeah, then I read my still.
Just there. Earlier there, but maybe the really nice solo. Okay, 2 more minutes, then we touch on this question. Anyone wants to speak?
I don't know what's the difference. Like,
what's the relationship between one that rotates clockwise and one that rotates anti-clockwise? That's all you need. Like you don't have to know like why 15 degrees. You just need to know what's the relationship between y and z. Right. You're right. Okay, well, you're correct. Like just control whatever it is. Don't try it. Okay, come. I think let's go over this question. Okay, then we can take a break first because later got still got questions. Okay. Answer for part 2, reagents and conditions is electrosub. So you just need to introduce your benzene, the appropriate catalyst, and finally warm. Okay, benzene, default benzene use warm. Okay, the catalyst here must suit bromine also. Okay? FeBr3 also okay. In fact, if you use AlCl3, FeCl3 also okay, but just going to be Br. Okay? Now, I want to look at part 2, right? Okay, if you look at part 2, first of all, let's discuss this question now, guys. Apparently, W exists in 3 different types. Now, you look at W, right? First of all, is okay, they say something about rotating light, so it knows about enantiomerism. W, the moment you see this structure, is it chiral or not chiral? Your first instinct. Okay, W, yes. Okay, the moment you see the structure, what's your first instinct? Chiral or not chiral? Okay, it should be not chiral. Because why? It has 2 chiral centers, but yet it looks very symmetrical, right? Okay, so plane of symmetry will not give you a rotation of plane polarized light. So by right, that's your first thing. Then you go look at the question, right? Hey, yes, okay, that's structure X one, right? But then suddenly got Y and Z. What's going on over here? And what's the relationship between Y and Z? Rotate by the same direction. Sorry, rotate by the same extent, but different directions. They are enantiomers of each other. That's the relationship, guys, and that's your justification. Okay, why enantiomers? Because they rotate by the same extent, but opposite directions. And the idea is this, okay? Somehow you need to find a way to make this guy not symmetrical. Agree or not? Because currently he looks symmetrical. You need to find a way he's not symmetrical, then you get an answer. For Y, we already kind of know what the answer, right? Okay, he has no okay, he has an internal plane of symmetry, and as a result, he cannot rotate plane polarized light. Okay, that one should be quite obvious. Okay, but then the issue is why? How come got another one? How do we make this not symmetrical, guys? What should we do here? Guys, I want you all to look at the carbon. This carbon is what shape? Guys, the carbon here is what shape first? Tetrahedral, and tetrahedral is a 3D shape, right? So guys, remember, if it's a 3D shape, I want you guys to know that you can actually manipulate the planes. What does that mean? Okay, guys, if you take a look, okay, to draw X, to make this compound symmetrical, do you agree, right? I can just ensure they are both the same. To make them both the same, I can just position the solid wedges on both ends. So that's actually structure X, because if you can see this, right, okay, the moment I go through this once, the next time you will not get this wrong already, because you know the technique. Okay, so over here, right, they are both chiral, but yet it is perfectly symmetrical, so it doesn't rotate plane polarized light. But how do we draw Y and Z? Guys, what can we do here? How do we make them not symmetrical so that they are enantiomers? The wedges can change, right? Okay, as you can see here, if I put a solid wedge here, then what should I put next? Dash wedge. Now, is the compound symmetrical? It's not symmetrical. As you can clearly see here, this is not, there's no internal plane of symmetry, so it only has chiral centers and it will then rotate plane polarized light. Then what's Z? How do you draw Z? Z is the what of Y? Is the mirror image of Y, right? So go and draw out your mirror image, and then your job here is just to flip Z around. So I have to draw from the closer to the mirror first, then I draw the rest. Okay, so it should be the opposite of what you have here. Okay, so guys, take note. This carbon is this carbon, right? If this is dash, this should still be dash. If this is solid, this should still be solid. That's how you draw enantiomers. Enantiomers, you don't flip the wedges. Dash means dash, solid means solid. Okay, so then they are both one normal image, one mirror image, they'll both rotate. Can see that? Okay, so that's the justification in your answer also. I will introduce another scenario where you guys will see this. Okay, so go and take a look also. right? Another scenario where this is also quite common, right, is this structure over here. Now, on first glance, guys, is this symmetrical or not? It is very symmetrical, right, on first glance. Okay, so by right, should it rotate plane polarized light? No, okay, it shouldn't. Okay, because even though it has chiral centers, it looks like there is a internal plane of symmetry. But this is exactly the same as this question. There are actually three structures, and only one structure, right, cannot rotate plane polarized light. How do we draw this structure? What should we draw for this structure? The BR must be on the same planes. Okay, so same side, same planes, yes. Okay, you can either draw two solids, which I did up here, or you can draw two wedges. It's a two dash. It's okay. So this guy doesn't rotate, right? Then how do you draw the other two? You can just alternate the thing, right? It doesn't matter. That one doesn't matter. Yeah, whoever rotates positive or negative, don't care. Doesn't matter. You're not taught that. Okay, so this is one structure. You can see that. Not symmetrical. And then the mirror image, you just draw it flipped. Okay, so now this guy is facing this side. He's still a dash wedge. Take note, I'm never changing your wedges. Okay, this guy is still the solid wedge. So these two guys can rotate plane polarized light. Okay, so I'm just introducing another scenario for you guys to be more prepared. Okay? All good? Yeah. Then it's the same side here and here when I cut it. Oh, as in like. Or this side is not facing down, right? No, it's not. It doesn't matter. You cut half like that, you can see that both sides are the same carry. Same thing, yes. It's not same orientation, same thing carry. Yeah, you get what I'm saying? Yeah. It's like this side benzene, this side benzene. Then solid also. Yeah, okay, same things. It's not about same sides. I get what you mean. Yeah, okay, all good with this. Okay, we take I think we only have like 5-minute break. Okay, maybe come back about like, yeah, okay, 5 minutes. Okay, then we need to do one final question. Right? Why? Really, right? Yeah. Really? We finish up one final question. Okay, can you turn over to question 4? Please don't get arrested in Korea, man. You're actually gonna get arrested. Hey, come, question 4. Let's go. Very short question, okay? KSB, I need to go through this. Somewhere in this world, right, also making fun of English. Like, I don't know what does that even mean?
Nobody. Older brother.
Oh yeah, so imagine like you're another country. Some random group like your here, they're like brother, they start laughing also. So the same idea.
No, it's not.
But from what I had to remember whether I got any Indian students here. If not, I'm gonna get cancelled. My next class all Indian students, so lucky enough to see. Hey, come faster. Question 4. Finish, you're done already. Finish, you're done. It's for your talking their language. You're gonna fun. You're gonna get fun. You just told me. Oh my God. Oh, you're A-levels, do that question. Stop calling me a nick. Say more, you will get cancelled, and I'm not gonna fail you out. So when the time comes. So do the question. This question. Okay, minimally, right? I need you guys to do part 1 and part 2. Part 3, don't know, we'll do together. Okay, that one's a bit more challenging. Okay, but part 1, part 2 must get correct, right? Okay, for part 3, perhaps you can just read it or you want to try a little bit also can. Okay, but I'll give you guys like 5 more minutes. Okay, let me faster settle this. Right.
You know now we have so much content. Imagine after this conference. So much content, none of them are seasonable.
Oh, and there's a way to say the people here are damn hot. You say the water here is damn good. I watched before. Because it's like basically they say the water is good, they drink, they become everything.
Well, like primary two, I think you have the call that call or the uncle, you're very good in give discount. This is really hard. Where I know it. Yeah, no, I
No,
know.
I don't know. That's cheap. Right.
What are they?
Next Sunday, yeah. Is that the group consult session? Yeah. Final time.
Oh, Vega is you. Vega is you.
It's the same thing.
Hey, 1 more minute, 1 more minute. Okay, make sure you at least do part 2. Okay, part 3 you'll do together.
No, do not do it.
Yes. Part 1 is the common iron effect. They added a common iron. Well, you this quadratic one. So what do you get rid of? Let's get rid of something. Because the damn small value. Nope. Something like this. So DT is very small. So you can get rid of this S. Once you get rid of it, this is going to yeah, proximity. Yeah, and also as in you will get one, but then you have to get rid of it.
Oh, right.
Part 3 answer is 1.17 times 10 to the power minus 5. Not easy to calculate that part. Yes.
So 1.07.
1.17.
Oh my god.
You get it?
0.9 way.
That's very far. Okay, come. Then let's go over the answers up. Right. Again, I just wanted you guys to try part 1 and part 2. Okay, part 3 is a harder question. Right, okay, come, let's take a look. Right, okay, part 1 is a common ion effect calculation question. This one, you guys should know how to calculate already. Okay, Ag plus now got two sources. Ag plus can come from AgCl, which is represented by S prime, and Ag plus can also come from AgNO3, which is 0.005. You must sub all these into your KSP, and then just assume your S prime away, so you don't get a quadratic expression. Okay, there, right? Okay, then that's your concentration. Now take note, right? This question, you must highlight the word until no more AgCl dissolves. What does this imply? Saturated solution, right? So a saturated solution implies, right, that the concentration of Cl minus is the same as its solubility. That's why S prime and Cl minus is the same. You can see that? Alright, again, that's how I get my answer. Okay, the next thing that we're going to use to discuss, right, is part 2. Okay, part 2 is about complex ion formation. They already told you guys. Okay, this complex you never see before, but they tell you it's a 1:2 ratio, so you just react something like this. Now remember, our forming complexes is always a reversible arrow also. It's just that the POE lies very far to the right. You're favoring the formation of the complex most of the time. Okay, but still use a full reversible arrow to discuss. Okay, that's the formula of the complex. You can guess one because they say 1:2 ratio. And furthermore, the charges, let's go and balance the left and the right. So you know the charge is -3. Okay, this. Okay, come up with these equations first. I need two equations to discuss. Okay, your job here is to then talk about your IP and KSP, right? Okay, so this one explanation wise should be okay also. Guys, when you add S2032 minus, you form the complex causing what? Okay, guys, take a look. Okay, you add the S2032 minus, you cause Ag plus to drop. Now, when Ag plus is less, what will happen? When you have less Ag plus, it will force this guy to shift to the right and dissolve more, right? You have to produce more, you have to dissolve more AgCl, okay, to reproduce a little bit more Ag plus. Okay, you can see that, right? Okay, but once you have done that, okay, then your AgCl solubility will increase or decrease. Okay, does it become more soluble or less soluble? More soluble, right? Okay, yeah, that's the answer to this question. Okay, so very quickly, right? Okay, your answer should just be about writing about the complex first. So go ahead and quote the formula in your answer. Okay, when the complex is formed, concentration of Ag plus drops, which causes IP to drop below KSP. So take note, right, guys, this is a KSP question. So you need to talk about IP lower than KSP. Don't just tell me about position of equilibrium. You want to tell me both is okay, but you must minimally tell me IP less than KSP. And when that happens, right, then you can tell me the solubility increases. Keep your answer short and sharp. Okay, there's 2 marks. Okay, 1 mark for equations, 1 mark for the explanation. Okay? But we're going to have to use this idea for part 3. Okay, part 3 is a bit more challenging. So I really need you guys to follow me okay, in part 3. Okay, we have to cover this quite quickly already. Okay, so I read through question 3 first. I want you guys to take a look at this question. Okay, I think this is a worthy question to discuss. A lot of the times, right, okay, they rarely ever ask us to calculate your complex ion formation. But here, they are asking us to calculate this. Okay, so it's possibly your first exposure, right, to complex ion calculations. Okay, but all okay, part 2 first. Okay, if you go ahead. Once you understand part 2, right, okay, then we can move on to part 3. Okay, part 3 is the same principle. It's the exact same reaction happening. You can see that from the question. It's the exact same question, but now with numbers. Okay, the only numbers that they have given us are these. Okay, so can you all see, right? If you take whatever you added, which is 7, whatever that's undissolved, you minus it off, you can get the amount dissolved. Can see that first? Okay, I think that one everyone can see, right? All good with that first. But is this amount of AgCl dissolved the amount of Ag plus used to form the complex? Is it the same thing? I hope you all realize that this has two parts. The AgCl that dissolved in total, right? First of all, can you all just ignore the second equation? The Ag plus came from AgCl first, right? That is your S and S. Can you see that? Because saturated solution, no second equation. So meaning to say, it first dissociates Ag plus to form a saturated solution, which is S. Can you see that? But then, right, when you add this complex, what will happen to Ag plus? Drops. And when it drops, your POE shift to the right? So can you see you're dissolving more AgCl? So there's actually another part to this. There's also Ag plus, right? That's used to replenish the ones that are disappeared to form the complex. Okay, so there's Ag plus to form the complex. I call this X. So can you all see, right? This value, right, is actually both S plus X together, right? Okay. So it's not fair for us to just use this value and conclude that it is used to form the complex, because not all of it is used to form the complex. Can you see that? And before I proceed with the calculations, I'm going to use easier numbers to showcase this. Okay. Now don't copy anything. Look up the board here. Okay, this one need to follow. First of all, I'm going to say there's 5 AgCl. How much Ag plus and Cl minus will I have? Saturated solution. 5 also, right? Okay. I write down here 5. Saturated S and S. I just use the number 5. Big, nice number. Okay. Now I'm gonna add 4 thiosulfate. What's gonna happen? How much Ag plus does it consume? 2. Okay. If I consume 2 Ag plus, what will happen to my Ag plus now? Left with how many? 3. Okay, guys. First of all, before I proceed, what was the KSP of AgCl? No, as in use this example. Ag plus times Cl minus is just 5 times 5, 25, right? Now your KSP will not change. It must be at 25 still. Currently, if it now reduces to 3, then what is it? The what is 15? The IP is 15, good. And it's less than the KSP of 25. So what will happen now when IP is less than KSP? It has to dissolve more. The POE must be forced to the right, such that Ag plus the ions will increase back up to what? The ions must increase it back to KSP of 25, right? Basically, your IP must reach back KSP of 25 again by dissociating more ions. Can you see that? So you want to increase the ions again such that you get a product of 25. So this one must increase to what? Yes. Can you see it cannot increase to 5? Okay, I'll show you all why. A lot of you guys will say, yeah, just bring this guy back to 5, then 5 times 5 becomes 25, right? Why is that wrong? Why is that wrong? Cl will also dissociate, right? Okay, let's just say, how do you bring this guy back up to 5? Okay, 2 more, right? So if you want to bring this guy back up to 5, you have to dissociate how many more AgCl? 2 more AgCl. But at the same time, you produce 2 more Cl minus. So now Cl minus becomes 7. 5 times 7 gives you what? Is that equal to the KSP? No. So I want you all to take note. You don't add back the number of Ag plus that's used to form the complex. Okay, because Cl minus also contributes to the equilibrium. So instead, what we're going to do here is I'm only going to dissociate 1 more AgCl. So how much Ag plus is there now? 4. How many Cl minus is there now? 6. 4 times 6 is pretty much 25. Can you see that? So what's gonna happen? What happens here is that there's 5 AgCl dissolved at the start, and 1 additional AgCl that is dissolved also because of this complex thing. So can you see what's happening here? How much AgCl dissociated in total throughout this entire this question? How much AgCl was dissolved? 6. And can you all see, right, that the 6 AgCl will be the same as the 6 Cl minus? Because Cl minus was not touched. Whatever CL minus there is, it's the same as total AGCL. Can see that? So we're gonna use this part to actually calculate our answer. So can you see this? I can find out how much AG plus, right, is not used in the complex. I can take the KSP of 25 divided by CL minus to give me AGCL not used in the complex. KSP is 25, CL minus is? What's the CL minus? 6, and the answer here is, let's just say 4. Okay, so if there's 4 AGCL not used, how much AG plus was there in total? Total AG plus is how much? 6, right? Okay, should be 6 in total because that's the total amount of AGCL that you dissociate. So you have 6 AG plus in total. How do you find out how much AG plus is used in a complex? How do you find out? I have total and not complex. So how do you find out how much complex? 6 minus 4. It's 2. Did I use 2 AG plus for the complex? Yes, I did. So that's how you calculate this question. I'm gonna now put in the actual values. Okay, so you all follow these steps. I'm gonna follow the exact same steps. Can you all see this AGCL dissolved in total is this part over here. Okay, how do I find the AG plus not used in the complex? Okay, how do I do this? Take the KSP divided by concentration of CL minus. What's the concentration of CL minus? Okay, basically is this number both is the same, right? Because it's 6 and 6. The AGCL and CL minus is the same. So AGCL and CL minus is the same. But I have to divide it by 2.5 because I need to do this in concentration, so as you can see over here. And then I can get my AG plus that's not used in the complex. Okay, which in this case 8.789 10 to the power minus 6 mole per dm cube. Can see this so far? Okay, then what's next? I'm just going to follow this up. Okay, what's the AG plus used in total? I'm doing concentrations. What's the total AG plus? Where did I get this value from? Sorry. Okay, where did I get the AG plus total? Where did I get the 6 from? Okay, the 6 came from the total dissolved AGCL, right? So it's the total dissolved AGCL. Let me just very quickly convert this into concentration also. So I work out everything in concentration. Okay, what's this value here? Okay, someone just type, oh, okay, no matter. Okay, now what's my final step? Total not complex, I can find out whatever that's used in the complex. Okay, take total minus not complex. Can you get yourself your answer? Yeah, because the volume is the same throughout. Okay, I can minus away concentrations because the volume never changed. It's 2.5 throughout because you added solid at the start. So the volume never changed. Okay, again, if I show you guys just this working, none of you guys will understand. So I need to show you guys how it actually works first. Use these easier numbers, copy down the easier numbers also. These easier numbers will make sense, right? Make more sense than that, of course. Okay, so don't attempt to understand the raw working. Attempt to understand this first. Then the raw working is just you suck all these into real numbers. Can see that? Okay, so understand this. Okay. But once that's said and done, that's it for today. Okay. Okay, I just go through this one more time. There's 5 of these. Dissociate to 5 and 5. Right? But I introduce 4 complex, so it uses up 2 AG plus. So the 5 drops to 3. See that? When it drops to 3, you need to dissociate more such that KSP is back. The IP is the same as KSP. Right, equilibrium, you need to dissociate to the right. I dissociate only 1 more, such that this one becomes 4, 3 to 4, 5 to 6. So 4 times 6 equals 25, pretty much. Okay. So basically what we calculated is I got the total AGCL dissolved. That's what the question gave me. Okay, that is the same as CL minus. I can take KSP divided by CL minus, 25 divided by 6 to give me 4. Now this AG plus never took part in the complex. is just there in the solution. Who took part in the complex is just these two guys. So I can find out who was not used in the complex. I also know what's the total. Then I can take 6 minus 4, give me 2. That's my final answer. So that translates into these 3 steps. Is what I did over there.
You say the best use to change the mode.
If you change the mode, you must change it back to concentration. Because at the end of the day, right, when you do this, TSP must use concentration. Right? Okay, so I change everything to concentration. Because thankfully, the volume here doesn't change. Okay, if the volume doesn't change, I can work out everything in concentration. You see, they give you 2.5 dm3, right? But they added solid, so the volume is still 2.5, right? Okay, so the idea is that if you want to work out in moles, can, but there's a lot more conversions to be done. Okay, any more questions here? Okay, whatever questions you have, okay, you can just ask me now. Okay, lesson end already. Okay, we are done, right?
How come you know like TSP there, but then you get that or not?
Okay. This guy using the complex only 2, right? Okay, so this guy out already. Okay. So I initially have 5 each in class. 2 of which go to form complex. So the 3 is it used in the complex? No. The 3 increased to 4, right? Did this participate in the complex? Still no, right? So that's like 4 is not in the complex. How do I find out this value 4? Let's take the TSP divided by CL minus. TSP is 25, divided by 64. I'm not using complex. Who using complex is the 2 roots over here. You see that? So you break it down first. Start with 5. 2 guys out to form complex. The 3 guys sitting there like, what the hell, right? Nothing happening here. But the 3 suddenly become 4. Okay? It's still not using the complex. Well, just introduce some easier numbers. I randomly choose 4 here, so that the number here is 2, so it's a nice number. I can introduce any number, but I choose these numbers because it's easier for you guys. Yeah, I just put these nice numbers so that you all can easily understand. It can be any numbers, then it can be any numbers. Okay, but I purposely choose these numbers so it's easier to process. Right? Okay, I choose easier numbers here for a reason. If I just show you all the working there, you won't understand. Very difficult to process. So you have to segregate between who is using the complex and who is not using the complex. Okay.
I saw a video.
Any questions? Okay, I understand this is a bit challenging. Okay, slowly go back and look at it again. Recite yourself with these easy numbers. Don't go and try to attempt to understand that. I cannot understand shit. That one, right, is after I come up with the easier working, then you'll change all these easier numbers into the harder numbers. Okay. Yeah, all these numbers for a reason. That's why I cross out, I don't erase. It is so slowly go and look at it. Right?
This is not all fun.
It is a tough question, undoubtedly.